I'm going to show you very quickly how to copy and paste a table of data from Excel into Geogebra, and how to do a regression analysis, like fit a model to the equation really quickly, like how to get Geogebra to actually find the model for you as opposed to you just working it out yourself. Okay, so first of all, you've got to open Geogebra. So put this down here. So open Geogebra. Hopefully you've created an online account already. If you haven't, you probably want to do that. So create an online account. I'm doing it with just the regular one. So sign in. Okay. I'm already signed in, so I'll just go here. All right. Okay, so you've signed in. You've opened up Geogebra. What you're going to do is you're going to go to a new Geogebra math calculator. Here's our Geogebra math calculator. So I'll just click out of there. What I need to do is I'm going to enter my data into a spreadsheet. So in order to do that, I need to open up a spreadsheet. So this little, see how I went to this menu thing? Sometimes if you click up on this menu, you can go to view. And I want to view the spreadsheet. So see, now I can see my spreadsheet if it wasn't already visible for your copy of Geogebra. So my data was already in a Excel spreadsheet. If it wasn't, you can manually type it in yourself. So just showing you, if it's already in a table somewhere in a spreadsheet, you can copy and paste it. You can always type it in yourself. Like, see, I can type it in myself, no problem, put in the numbers, but I can't be bothered typing it in. I just want to copy and paste my data. Oops. Did that copy and paste in once? Yep, it did. Okay, so see what happened? It kind of popped up over here. I can just delete it. Right click, delete. These things are a pain too. Delete them. They're not there doing there. Delete. 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 So those points weren't meant to be there. That's great. Okay, but what I am supposed to have is these points up here. So here's my table. It's just as easy to manually type it in, but if you've got a big long list of data, being able to copy and paste it in like this is really handy. Notice that I select it. So I've selected it first. Then I've gone over to here. I'm creating a scatter plot. 1, 2, list of points. Call the list whatever you want. My list 1. Call it whatever you like to call it. Create. See, here's my list of points. See, it's made a nice little scatter graph. You can adjust the axes if you want. That's okay. That's easy to do. I've probably shown you in another video how to do that. So now I'm going to show you how you can try to fit a model to these points, how to really quickly do that. So notice I've sort of selected my data again, selected the data again, and when I did that, this little thing up here popped up, a graphy thing. So a little bar graph. We're doing a 2-variable regression analysis because we've got X data in the first column, column A, Y data in the second column, column B. Here it is, and see this new window pops up. So now my scatter graph is appearing over here instead. And I can choose what kind of model I want to do. Now let's see. So imagine the most simplest one is a linear model. Let's do, so see I can select which one I want from this menu, linear. There it is. Here's my linear model. And it's kind of fitted. It's kind of got a little regression equation down here, y equals mx plus c, so gradient's 1.2, y-intercept is 2.6. Imagine I wanted to know some other data from it, so if I click on this little sum thing, some really handy things pop up. So see, it's kind of compressed my little graph. It's got the mean of x has popped up, the mean of y, my weight, so mean of x, the mean of y has popped up here. S of x, that's the standard deviation for a sample. So the standard deviation for a sample of my x data is S of x. S of y is the standard deviation for a sample, not for a population, but standard deviation for a sample of my y data. I also have my R value, my Pearson's correlation coefficient here, so 0.9649 is my R value. And some other things that might be useful, might not be useful. Put another thing down here which is useful. It's called the coefficient of determination. That's your R squared value. So basically it's my R value squared. Okay, so coefficient of determination is useful if you're looking at other models. The Pearson's correlation coefficient is for a linear regression, but if I'm not doing a linear one anymore, I'm doing other sorts of regressions, I might want to look at the coefficient of determination instead. Alrighty, so there's my linear model. Imagine, So notice that the data is kind of pretty curved. It's kind of, you could use a straight line model. Maybe you want to investigate a different kind of model though. Maybe a quadratic model, like it could be an upside down quadratic. So we could go to polynomial. Polynomial, so notice automatically it's made a quadratic graph and so on. I've still got my mean of x, my mean of y is all still calculated. But notice my r squared's changed. I've got a different r squared value because it's a different model this time. So that's kind of interesting. So just showing you when we go from linear, see the same mean and the same standard deviation and everything is still there, but my r squared's changing, isn't it? So polynomial. So if I wanted to investigate a cubic instead, so this is the degree of the polynomial. So if I've selected 2, degree 2, that means my polynomials are quadratic because the highest power of x is a square. Here's the model, by the way, the quadratic model that it came up with. Quadratic regression. If I did a cubic regression instead, this would be my cubic model. So it just always resets back to 2 here, but notice it's a cubic model. Different r squared value again. What if I did a quartic instead? Here's my quartic model. Here's the equation for that model. Got a different r squared value again. If I did a quintic, it's my quintic model here, and here's the graph, and so on. Cool. So notice you can do other sorts of models. You can do exponential model. Exponential model doesn't seem to really fit the graph very well. Would you agree that it's kind of, if anything, the data is a bit more logarithmic? So instead of an exponential model, notice a different r squared value from an exponential model, and they're using e as the base of my exponential model. And if I did a logarithmic model instead, notice they're using the natural log. So it sort of fits kind of okay. Here's my logarithmic model, 1.63 plus 5.01 ln of x. Logarithmic model, different r squared value again. Sine model, it's our sine model, trigonometric model. They've done 5.46 plus 7.58 sine, so on. What else have we got? There's other sorts of models. There's logistic models. And what else have we got here? Power models. So it's a power model because, there you go, x to the power of something. Here's that model. Trigonometric model, as you can see, has got a sine in it. Growth model. Have I gone through them all? I've actually gone through most of them. Yeah, I think I have. And polynomials are varying degrees. So see the highest degree it seems to go up to is 9. So 9, meaning the highest power of x is a 9, x to the 9. Going back to the linear one again. Here it is. So that's basically kind of like how you come up with, do a regression and explore different kinds of regressions, and can really easily get some calculations from these. You might also want to copy to graphics view, or export as a picture. That might, if you've got a model that you want to investigate further, or copy it into your assignments or something like that, you can choose either of these options. So that, notice that was kind of going up to here. Scatter plot, I can also do a thing called a residual plot. So notice if I kind of like basically calculated the distances from each point to the line, the vertical distance from this point to the line, this point to the line, and so on for all the points. If I measured the length, the distance, the vertical distance between where the x value would be on the regression line and where it would be on the actual point, and plotted those, we would get a thing called a residual plot. So depending on what investigation you're trying to do, you might be interested in getting these residual plots. So let's see. We did a residual plot which kind of came out as looking a bit like a quadratic. Let's do a polynomial plot. I'll try to take it back to degree 2 again. Oops, doesn't seem to want to do that, does it? Okay, so something's just gone a bit wrong with my little model. I would just have to, I've just been messing around with it too much. Oh, it's because I'm on residuals, that's why. Okay, sorry, going back to linear, I forgot to take it off, back onto scatter graph. I was confused by why is it looking like that. So polynomial, degree cubic, I wanted degree 2. So back to a quadratic model. Doesn't seem to want to go to my quadratic model though, which is interesting. Okay, if that's the case for you, then just, I would say, just start again, start this whole thing again. that doesn't seem to want to go back to a quadratic model for me. But if I wanted to investigate the residuals, there's a residual analysis of that cubic. I wanted to see a residual analysis of the quadratic that we had, but it's kind of like locked out of doing the quadratic again. So see, residual plots are useful if you're looking into residuals. Okay, so I might just finish up there for now.